Hola, Mr. Sutton here with the BC Calculus 8.1 Part 2 homework solutions on parametric functions. On this problem, we're given x equals t squared minus 1 and y equals ln of t, so parametric pair of functions here. We want the second derivative in terms of t. We're going to have to start by finding the first derivative, dy over dx. To get that, we're going to need y prime over x prime. So that's going to be 1 over t for y prime. X prime is going to be 2t, and then that 1 gets differentiated away. And we're going to simplify this a little bit because we know we're going to need another derivative. So let's see, this t can move downstairs. We end up with 1 over t squared, or I guess you could write this as 1/2 t to the negative 2. That would probably make it easier to use the power rule later on. So now for the second derivative, I'm going to need the derivative of this first derivative here in terms of t, but then I'm going to need to divide that by x prime again, by dx over dt. So derivative of this stuff in terms of t, multiplying by 2 using our power rule, that's going to be negative, those cancel, so negative t to the negative third. But then we have to divide by x prime again, so this 2t down here. And that doesn't look like any of the answer choices, but we're going to simplify it a little bit. I can move this t downstairs to be a t cubed down here. So I'm going to end up with negative 1 over 2 t to the fourth. And that is going to match one of the answer choices, choice A. For this problem, position of a particle moving in the xy plane is given by this set of parametric functions here. Actually, these are their derivatives. We want the slope of the line tangent to the path of the particle at time 2. All right, so they've actually given us most of what we need here. We're looking for dy over dx evaluated at t equals 2. To get that, just using our normal parametric setup, we're going to have y prime of t over x prime of t. So in this case, that's going to be y prime of 2 over x prime of 2. And since they gave us these functions, we're just going to enter this in the calculator. So here's what I've got entered in my calculator. In my y1, I've got the x prime function. In y prime is going to be in the y2 here. So now quitting out of there, I'm going to do, let's see here, fancy fractions. So alpha y equals, and then option 1. And then I want, let's see, alpha trace. I want y2 in the upper part here because I need y prime of 2. So I'm going to do y2, open a parentheses, put a 2 in there. That basically does y prime of 2. To get x prime of 2, I'm going to do alpha trace, and then I need y1. So let's see here. Alpha trace, there we go, y1. Put a 2 in there, and just press enter and watch the fun. There we go, about 1.107 that rounds off to. And that's going to be choice B. On this problem, we want to know what value of t gives our parametric set of equations here a vertical tangent. So if we're looking for vertical tangents, we're looking for a place where there is vertical movement but no horizontal movement. So in terms of parametric equations, we want the derivative of x, the x prime, to have a value of 0. And we want y prime to have a value of really anything except for 0. So let me start by figuring out what x prime is and setting that equal to 0. So x prime, that's going to be 3t squared minus 2t, and then that 1 is gone, becomes a 0. So I'm going to set this equal to 0 now. And in order to solve this for t, and this is a no calculator problem, I'm going to have to factor a t out of here. So that leaves me with 3t minus 2 equals 0. Setting each of these factors equal to 0 and solving, I see that t has a value of 0. And also, if I add the 2 and divide by 3, this is going to be 2/3. But I can't just check these, accept these blindly without testing them. I need to make sure that both of these give my y prime a value of something other than 0. Because if y prime of these things comes out to 0, then that means I've actually found a place where the particle is at rest, which is not the same as having a vertical tangent. All right, so let me find y prime then. That's going to be 4t cubed plus 4t minus 8. And let me plug each of these in now. If I plug in 0, so y prime of 0, well, all of this is going to come out to 0 except for the negative 8. Most importantly, that's not 0. So that means that we have a vertical tangent line at t equals 0. Now we have to also test 2/3 because there's an option for 0 only. So for 2/3, plugging that in, I've got 2/3 plugged into really all of these spots here. And this is going to be a little bit more annoying to calculate, so let me take it term by term. This first one, cubing this fraction, I have 8/27 times 4 gives me 32/27. For this next one, 4 times 2 is 8/3 is 8/3, and then we're subtracting 8. So you don't actually have to calculate the exact value of all this to see that it's not going to be 0. 32/27 is a little bit more than 1. 8/3 is a little bit less than 3. If you add a little bit more than 1 and a little bit less than 3 together, you're not going to get anything even close to 8. So subtracting 8 from these is going to give us a negative number, certainly is not going to give us 0. So we've seen enough to conclude that we also have a vertical tangent line then at t equals 2/3, which means we can pick answer choice C. On this one, between times 0 and 13, we have an object going along an elliptical path, and here are the parametric equations associated with it. At the point where time is 13, the object leaves the path, so I guess you could think of like swinging something around your head and then letting it go, and it travels along this line tangent to the path. We want the slope of that tangent line. So we're basically looking for a parametric slope. So that means we need to do dy over dx equals y prime over x prime of t. So we need to calculate these each individually. This is a no calculator problem, which the answer choices kind of make clear. So for y prime, taking the derivative of this expression here, that's 4 cosine of t. And then for x prime, derivative of 3 cosine of t, that's going to be negative 3 sine of t down there. And we essentially have to plug in 13. They said at time 13, so we have to plug that in for t. And I'm actually going to simplify this a little bit here. This will be negative 4/3, and then a cosine over sine, that's cotan. That would be a good thing to do right now. Make it easier to plug it in, so I only have one place to plug something in rather than 2. All right, so now plugging in 13, this is very simple. We just do negative 4/3 cotan of 13. Of course, that doesn't match any of the answer choices, but here we have to remember that cotan is really 1 over tan. So I can rewrite this as negative 4/3 tan of 13, and that does match answer choice D. For this problem, curve in the plane is defined parametrically by these two equations. We want the equation of the tangent line at time 1. So tangent line, you need an x value, a y value, and a slope. Let's start with the x and y since we already have equations for finding those. For the x value, we're just doing x of 1, so that's going to be 1 cubed plus 1, and that just adds up to 2. Now we need the y value at time 1, so that's going to be y of 1, which is 1 to the 4th plus 2 times 1 squared. Well, that's just 1 plus 2, which is 3. So we have the point 2, 3 that we're going to plug in, and we're also going to need a slope to go with that. Now they gave these to us in slope-intercept rather than point slope, so we can't use 2 and 3 to really narrow this down at all. So now for my slope, I've got dy over dx equaling y prime over x prime of t. Y prime of t, taking the derivative of the y function here, that's 4t cubed plus 4t. And then for x prime, that's going to be 3t squared plus 1, using my power rule here. And I have to actually plug in 1 for time now to find the slope at time 1. So plugging in 1, we've got 4 times 1 cubed plus 4 times 1, all over 3 times 1 squared plus 1. So 1 plugged in to all the places where t was. In my numerator, this is 4 plus 4, which is 8. Denominator, this is going to be 3 plus 1, which is 4. 8 over 4 is going to give us just 2 for our slope. Now we have to go back and actually plug this in. So I'm going to use the point slope form. Just using the slope of 2, you can narrow this down to answer choices A and C, but I don't know what the intercept is going to be. So using y minus y1 equals m times x minus x1, I've got y minus the y value 3 equaling our slope of 2 times x minus our x value we found of 2. And that does not match the answer choices because it's not in slope-intercept form. So I'm going to do a few things here. First, I'm going to move the 3 over to the other side of the equation, so I just have a y equals on the left. We distribute the 2, that gives us a 2x, and we'll also have a minus 4, but remember I added 3 over here, so this is really going to be minus 1. And that is going to match answer choice C. On this problem, we're given the parametric functions for x and y, and we want dy over dx. So in general, for parametrics, that's going to be y prime of t over x prime of t. So in particular, y prime of t here, that's going to be, let's see here, using the chain rule, cosine of 2t times a tail of 2, so 2 cosine of 2t. And then for x prime, we've got e to the 2t also times a tail of 2, so that's going to be 2e to the 2t. And there really isn't much else to do here except reduce this by canceling these 2's. So we have cosine of 2t over e to the 2t, and that's going to end up being answer choice E. For this problem, we're given the parametric equation for x and y of t, and they want the second derivative. So in order to figure this out, we need to find dy over dx. So that's going to be, in general, y prime of t over x prime of t. In this case, y prime of t, that's going to be 4t cubed, and then that's just plus an invisible 0. Downstairs, we've got the derivative of x of t, which is going to be 2t. And we can reduce this. We probably should, just so we're not dealing with it later on. So this is going to be 2t to the second. So now to find the second derivative, we need to take the derivative of dy over dx in terms of t, and then we need to divide that by dx over dt, or x prime, basically. So that's going to give us the derivative of 2t squared, which is 4t, over this x prime again, so 2t down here again. And that just reduces to 2, giving us answer choice B. For this problem, we have an object moving in the xy plane with its position at time t given by this pair of parametric equations. We want the rate of change of y with respect to x, so in other words, dy over dx, when t equals 3. So we're going to get a formula for dy over dx, and then we're just going to plug 3 into it. So to do this in terms of t, we have to do y prime of t over x prime of t. Y prime of t, that's the derivative of this square root function. This is originally t squared plus 16 to the 1/2 power. So we're going to use the chain rule here. We have 1/2 or something to the 1/2 power. So the derivative of that is going to be 1/2 times the something to the negative 1/2. So 1/2 t squared plus 16 to the negative 1/2 times the derivative of the inner function. So that's going to be a 2t tail that we're multiplying by. That's all y prime. X prime, we've got the derivative of this polynomial. So that's 3t squared minus 6t, and that 2 gets differentiated away. Okay, so now we're going to have to go ahead and plug in 3 to this mess here. So when I'm doing that, I'm going to rewrite this with fractions and radicals. I'm going to have a fraction for sure. And in the numerator, the only thing, if you look closely, that's left in the numerator is this 2 times t. So that's going to be 2 times 3 that I have in my numerator. Coming downstairs, this 1/2 can, the 2 and the 1/2 can come downstairs here. And then we also have this whole parentheses with a negative 1/2 power. That's the square root of t squared plus 16 coming downstairs. So that's going to be square root of 3 squared plus 16 down there. And then finally, this 3t squared minus 6t was already there. So we've got 3 squared minus 6 times 3. And that's going to be in a big parentheses here. So in the numerator, I've got just 6. Denominator, I still have that 2 down there. And then this is going to be 9 plus 16, 25, whose square root is 5. Over here we have, let's see, this is 3 times 9, so 27 minus 18, that's 9 that came out of that brackets there. Of course, we have to reduce it to get one of the answer choices. So 6 over 2, that can reduce to just 3. And then so we have 3 over 45. 3/45 reduces to 1/15, and that ends up being answer choice B. For this problem, we're trying to find the highest point on the parametric curve represented by these two functions over the interval from 1.5 to 4.5. So in order to do this, we need to take a derivative, specifically of the up-down motion variable here, y. So we need to figure out where y prime of t equals 0, and then we'll test around those critical values and figure out, basically what's the highest point based off of this. All right, so let's go ahead and do y prime. That's going to be negative sine of 2t times a tail of 2, so negative 2 sine of 2t. And we need to figure out where this equals 0. Now I could do this on my calculator, but it's not that hard to do this algebraically. So divide by negative 2, and we have to take the inverse sign. Where is the sign of something? Where is the y value on the unit circle equal to 0? Well, that's going to be at 0, pi, 2 pi, every multiple of pi basically. Looking at my numbers here, probably pi and 2 pi are some good ones to have, but I could keep going if I needed to. And remember that when I do inverse sine, I now have 2t equals all this, not t itself. To get t itself, I have to divide all the answers I have over here by 2. So that gives me pi over 2, and 2 pi over 2 is just pi. Let me just quickly verify that these numbers are between 1.5 and 4.5. Pi over 2, that's about half of 3.14, which should be between these numbers. Pi itself is 3.14, so that's good. And if I went any higher, I'd be adding like another 1.7, so that would give me something outside of my range here. So these are the only numbers I really have to check. All right, so I need to test out these. I also need to test out possibly the endpoints. Let me actually go ahead and graph y prime and see what it looks like on the interval from 1.5 to 4.5. So I've got the y prime of t here entered in my y equals, and for my window, again, I'm using 1.5 to 4.5, and let me do a zoom 0, zoom fit, see what this comes out to. All right, so here's my y prime, and I see that it's unfortunately crossing the x-axis multiple times, so I can't just pick one and say, hey, that's the only critical value, so that's all I'm going to use. I have to test the critical values, I have to test the endpoints, so let's get down to it here. And I'm going to have to test them in y of t here, cosine of 2t. So let me actually go ahead and enter that function in. So we've got cosine of, and I'll call this 2x on my calculator. All right, let's quit out of there now, and we've got a few things to test. So we have y of 1.5. Testing that out, let me do alpha trace and then pull up y2. Open parentheses, 1.5, and that's going to come out to about 0.9, let's see, 90 if we round that off. All right, we need to also test out, I guess the next number would be pi over 2. Now, this one you don't necessarily need a calculator to test out. If you're testing this out up here in the cosine of 2t, this is really going to be cosine of pi, and that's just going to be negative 1. Next, we have to test out y of pi, and that's going to be cosine of 2 pi, which comes out to 1. We're on the right half of the unit circle there. Finally, there's my other endpoint, 4.5. That I will need the calculator for. So going back to my calculator, I'm going to arrow up to my input from before and press enter to grab that. Let me just change this to a 4.5, and that comes out to about 0.911 and some change. So comparing these, I was looking for the highest point, so I want the one that gives me the highest y value basically. That's going to be happening at pi. So my highest point is at pi, so that's going to be the point, whatever x of pi and y of pi is. Well, we already found y of pi, it was 1. X of pi, if I plug pi in here, sine of pi is 0, 2 times that's still 0. So we have 0, and then the 1 that we found before when we were testing for max values.